Hey, so in this video, we're going to finally explain neural networks. This is definitely a buzzword that gets tossed around a lot in AI and ML, but they are really important. They're probably the most powerful form of machine learning to date. They are what ChatGPT uses. They are used in self-driving, deepfakes, image generators like DALL-E. Neural networks are a really important concept to understand. And I think a lot of resources online often really overcomplicate neural networks, right? Because you've probably seen a drawing like this before. Might see like 3 nodes in this first column, and then like a bunch more over here, and then maybe like a bunch more over here. And the idea is that they're all connected to each other like this. That actually took a while to draw out, but the idea is that all the nodes in every column are connected to all the nodes in the previous column, or layer, as they call it. But this is honestly an overly complicated diagram to understand, so let's start from a simpler example that we can still understand neural networks from. So in the first node, or the first layer, I'll draw 3 nodes, and we'll just go ahead and do 2 over here. And all the concepts are still going to apply, even though this is a simpler neural network. So we'll just finish drawing this out. And essentially what neural networks are is they're actually just basically multiple instances of linear regression, right? We've talked about linear regression before, and the main important concept behind linear regression is we have some sort of output number, some sort of function. In one of our previous examples, we talked about predicting the price of an Uber based on the time, the mile distance in miles, and the time of day, right? So maybe the price is a function of x, y, z is equal to w1 times x plus w2 times y plus w3 times z. And then we also might learn an additional bias or constant term, which we call b. And when we talk about training this linear regression model, it's just about learning the w1, w2, w3, and b that make this function work pretty well for new data points that it's never seen before. So this is actually all a neural network does too, except we have way more than just W1, W2, and W3. So the first layer of a neural network, the leftmost layer, is called the input layer. And that each node in that layer will actually have a number which corresponds to the input attribute. So let's say the distance goes here, the time length goes here, and time of day number goes here. So each of these neurons will have a number associated in it. There will be a number in this neuron, there will be a number in this neuron, and there will be a number in this neuron. And what each node in the following layer does, right? So this node here and this node here is, since each of those nodes is fully connected, right? Each of those nodes is connected to each of the input attributes. Each node is actually just doing its own linear regression, right? So in this node right here, it will have its own W1, W2, W3, and b that has to be learned through training, which is just gradient descent, taking derivatives, and then using the derivatives and the learning rate to update the weights. This node over here, completely independently of this neuron, will do its own linear regression. So this node will also have its own, W1, W2, W3, and bias. And then, well, the point of the neural network was to use it to make a prediction, right? That's all these AI models are about. But then you'll notice that we would have like an output number in this neuron and an output number in this neuron, right? So how would I actually use this neural network to get a meaningful answer, right? If I wanted to use this neural network as a way to predict the price of Ubers. Well, we might do something like average these two numbers. Average the number in this neuron, average the number in this neuron, right? So that might look something like this. So that's all a neural network is, right? We might take those two numbers in this output layer right here. We have a number in this node and a number in this node, right? But what we'll actually do is we will just send them into some average function, and then the number that gets kind of outputted by this function is our final prediction by the neural network. And then based on that number and whatever the correct answer was for these, for this data point, which consisted of 3 features or 3 attributes, then that would be used to calculate our loss or our error. And then we can kind of do something called back propagation. You may have heard this term before. It's okay if you haven't. But back propagation is just that process of calculating the derivatives, and essentially then we're going to use those derivatives to update our weights through gradient descent. So this is actually our first neural network. So then how does that kind of tie into this ugly looking diagram? Well, the same thing goes for the first input layer of the neural network. For whatever kind of data set this neural network is being used on, there must be 3 input attributes because we have 3 nodes in that first layer. Then each of these 4 neurons, this one, this one, this one, and this one, will learn a W1, a W2, a W3, and a B. And the B, or the bias, the constant term, is optional, but it will learn what those parameters are based on gradient descent. And then we'll basically notice that if each of these nodes, this one, this one, this one, and this one, are doing their own linear regression, right, then each of those are outputting a number. But each of these nodes in our final layer, right, the output layer, well, this node, this node, this node, and this node, and this node, right, they're all connected to each of those nodes in the second layer. So what that means is that each of these nodes, right, all of the nodes in the final layer are doing their own linear regression based on how many features or attributes are in the previous layer. And we have 4 there, right? We have 4 nodes in that second layer. So that means that this node over here is going to have to learn a W1, a W2, a W3, a W4, and an optional constant term or bias. And this one will have its own 4 weights and a bias. This one will have its own 4 weights and a bias. This one will have its own 4 weights and a bias. And this one will have its own 4 weights and a bias. And maybe for whatever data set this neural network is for, we're actually going to predict 1, 2, 3, 4, 5 output numbers, right? I don't know what data set this neural network is for, but we can certainly imagine a case where some model has to predict 5 different things, right? So, but if we only wanted to predict one thing, we would then maybe send this into some other function, like the average function, to get some sort of estimate of whatever number we're looking for. And that's all a neural network is. It's just linear regression stacked up vertically in each layer. Okay, so the only part really left to explain is how this would work in code, right? How would we implement this? So for our input layer, our 3 attributes, that we could represent that as a vector, right? Those attributes, x, y, and z, for a single data point, could be represented in a vector like this. And we know that each one of those nodes in that second layer has 3 weights, right? Because each one of those nodes is fully connected to each of our input attributes. So if we have 3 weights for each of those 3 neurons, we need to have a 3 by 3 matrix here to kind of encapsulate all those weights in a compact way. So let's draw that 3 by 3 matrix. And the last thing we need to remember, it's just a fact from linear algebra. If you need a quick refresher, the way we do matrix multiplication is we do the row of the first thing times the column of the second thing, right? And we know that this is ultimately going to give us something that's actually just 3 numbers, right? Because if this here on the left, right, we have 1 row and 3 columns, so it's a 1 by 3. Multiplying that by something that's a 3 by 3, these actually cancel out, and we're just left with a 1 by 3, right? And that kind of makes sense that we will have a 1 by 3 as the output, because we have 3 numbers, which is essentially like the output number for each of those neurons. People sometimes call that the activation of the neuron, so that's not a super important term. So in the first column of this 3 by 3 matrix, what we would have is we would have W1 for the first neuron. We'll say this is the first neuron. So that's W1 for the first neuron. So we'll call that W1, comma 1. Then here we would have W2 still for the first neuron, and W3 still for the first neuron. Here we would have W1 for the second neuron. We'll say that's the middle neuron in the second layer. Then this is W2 for the second neuron, and then finally we would have W3 for the second neuron. So in our code, we're going to have to maintain the state of this matrix. We're going to need to remember what all these weights are, right? So we're going to need to maintain that matrix, because when we do get model prediction and we're doing all these matrix multiplications, we're going to need the state of this matrix. And since we're going to calculate a bunch of derivatives with respect to each of these weights to update it, we're also going to need the matrix, right? And so there's one class in a library called PyTorch, which we're definitely going to have a whole separate video on, but that class is called nn.linear, and it will actually keep track of the matrix under the hood for us, as well as all the derivatives. The only thing we have to pass into the constructor of this class when we're making an instance of it is 2 things. Essentially, we just need to specify the dimensions of this matrix, and this class takes in something called in features. We can just call this inf for in features, and it takes in something called out features. So the input features for a given linear layer like this is just the number of features in the previous layer, right? So we can see in the previous layer, we had 3 nodes here, 3 features. That's what we would specify there. The number of output features is just the number of individual instances of linear regression. It's how many nodes or neurons you have in the layer that this class or object that we're making is for. And here we can see we also have 3 neurons there, so out features would be 3. So to do this in PyTorch, all we would do is make an instance of this class, nn.linear, and we would just have to pass in 3 for in features, 3 for out features, and that would be our simple 2-layer neural network that we have right here. One final concept we have to talk about before our crash course in neural networks is finished, and that is something that is completely orthogonal or different than linear regression. And it's literally the opposite. It's something called a nonlinearity. A nonlinearity, and the most popular one is something called the sigmoid function, which has this symbol. And if you were to graph that function, it essentially looks something like this. So we have our x and y axis here, and for every x input, right, like negative infinity is here, positive infinity is here, the outputs of this function are always between 0 and 1. So let's see, on the y-axis, we have 1 over here. And it looks something like this. It's kind of like that J-shaped curve. It's kind of asymptotically approaching 1 here and asymptotically approaching 0 over here. It's just kind of a terrible drawing over here, but pretend that it's going down. So the outputs of this function are always between 0 and 1, and it has this kind of nonlinear nature to it. So it's actually could be like mathematically proven that when we have those neural networks that we talked about previously, right, where all we have is these linear matrix multiplications, these linear connections over here, there's only so complex of a relationship that they can learn. There comes a point where their neural network isn't powerful enough anymore to capture and learn like really complex relationships. For example, like for a neural network to understand negation in speech if you were inputting sentences into a neural network. So we have to kind of add these non-linearities to the neural network to make them more complex and apply these neural networks to more and more problems. And something called the sigmoid layer, there is a class called nn.sigmoid, which you can make an instance of in PyTorch. That's kind of how we would do that in code. And the other benefit of adding a sigmoid layer to a neural network, and just to be clear as to how we would do that in a diagram, is literally right here, you have your neural network, right? There's 2 layers, the input layer, and we have 1 hidden layer, is what they call it, with these 3 neurons right here, right? This neuron, and this neuron. So what we would actually do then is just draw, say, the sigmoid symbol over here, put that in its own little circle of its own. What we would do is we would actually connect each of the previous layer's nodes to this sigmoid, because each of those 3 neurons in that second layer has a number, an output, people call it an activation associated with it, right? And for each of those, we're going to pass that into the sigmoid function to get something that's between 0 and 1. The higher the number is, the closer it'll be to 1. So scrolling down back here, the main thing we really need to talk about now is how you can apply the sigmoid function to a neural network. Not only does it allow you to learn a more complex relationship, but it allows you to apply ML and neural networks to more complex problems, right? Previously, we've just been talking about something called regression problems, where the output of the neural network is some number, right? Like the price of an Uber or how tall someone's going to be. And this is like a number that exists on a spectrum, right? There's no fixed set of values. But what if we are doing something called classification, right? Where let's say we need to build a neural network to predict whether or not someone will develop diabetes, right? You either develop diabetes or you don't. There's 2 classes. And maybe our neural network actually needs to output a probability that the patient inputted to the neural network will develop diabetes. That means our neural network needs to, if it's going to output a probability, it needs to output something between 0 and 1. Well, the sigmoid function is perfect for that, right? Because if we stick a sigmoid function at the end of our neural network right here, and let's say we were to average, before we pass into the sigmoid function, we average this number, and this number, then we pass that number into the sigmoid function, well, our neural network is now outputting one single number, right? And we can interpret that number after we've kind of done enough iterations of gradient descent and training to make these weights actually make sense for them to not just be random numbers. Well, we can interpret that output number as a probability that the input person is going to develop diabetes. So now we're actually able to do classification problems, right? We can classify an input into like say 2 classes or 3 classes as we talk about like more complex functions other than just the sigmoid function. The sigmoid function would just be used for binary classification because the output is just between 0 and 1. But we might be doing ternary classification if we wanted to build a neural network that can classify an image as either like a dog, a bird, or a human, right? But this is just one example of how we can extend neural networks by adding this nonlinearity over here to use it for something called binary classification for, say, diabetes prediction. And say the 3 features of the patient, like 3 markers of their health, like 3 facts about their blood work, might be one of them over here, one of them over here, and one of them over here. And of course, just one last clarification, we can obviously have as many features as we want in the input layer over here. We can have way more than 3 nodes over there if we need to. We'll just have 3 for this case. So that's an introduction to neural networks.